Hi, I'm Alex Ansari. I'm the TA of this Coursera course, and I'll be presenting the first half of this demonstration today. So far, you've all learned quite a bit about modeling engineered systems, but for the most part, those systems have been smaller, consisting of just a few components. So if I were to ask you to model something much more complicated, like the power grid, you'd probably feel a bit overwhelmed. Well, that's what we're going to be talking about today. We'll be describing how you can use the techniques that you've learned in this class to model the power grid from the point of view and by considering its main components. That is, we'll be looking at how power flows from generators through transmission equipment, distribution equipment, through transformers, and off to power loads distributed across the grid. By looking at how all these major pieces of equipment function and how they connect together, you'll see how large-scale phenomena like blackouts can occur and how the grid can respond to different types of disturbances. So we're going to start by developing some very simple mathematical models that describe these main components and how they connect together. So let's begin by looking at the power-producing equipment on the grid, that is generators. So a very simple diagram of a generator is drawn over here. It is a traditional generator. There's the rotor over here, which is usually powered by what's called a prime mover. Something like a large steam turbine will get this up and moving and spinning. So this rotor will spin. Generators usually have a lot of mass associated with them. There's a lot of torque required to get them up and spinning. And as the rotor spins, so let me draw it here at an angle, delta. As the rotor spins, you see it's attached to these magnets. So these magnets change location. Around the generator are all these coils. So as the position of the magnets changes, from Faraday's law, we know that a changing magnetic field will result in a changing electric field. So the position of these magnets changes, the electric field through these different coils starts changing, and we get voltage in the coils, and that induces current to flow out through any loads connected to the generator. So to understand how this phenomena occurs, we use the swing equations. These approximate how the mechanical power relates to the current that a generator produces. So under normal operating conditions, the swing equations, m term is just a constant, times delta double dot, which is the second time derivative of the rotor angle, or the acceleration of the rotor, has to equal P sub m, the mechanical power associated with the prime mover, minus P sub e, which is the electrical power. So two things that you should be noting from these swing equations is that, first off, they're very simple second-order differential equations, yet they provide good enough approximations that they're used by actual power engineers in modeling the power grid, which is surprising and great for us. The second thing you should notice is that they really make it apparent the connection between the electrical power and the acceleration of the rotor of the generator. And so if you imagine a scenario where on the grid you might have a transformer blow up or a line drop, or all of a sudden the electrical loads might change. Well, that results in this term swinging and changing possibly rapidly, and now you get these accelerations on the rotor that can be significant and can spike or drop. And so this puts a lot of stress on the rotor and can produce torques that can be potentially damaging. So engineers might have to shut down the generator. If this happens, this term, the electrical loads in the system, might change, spike, or drop. And well, when you shut it down, they'll jump up suddenly. And all the remaining generators might get stressed and have to be shut down one at a time. And so if this happens, you might get cascading blackouts. You can have different effects that we want to model and understand. So to do that, we're going to have to model how each of these generators now connects to the rest of the grid. So let's do that now. So here we have a generator, which is over here. And we're going to draw its connection just like you did. We're going to do a circuit diagram just like you did with DC, which is direct current circuits, which you've looked at earlier in this course. We've got the voltage that the grid is at, which is a voltage, and it's also at some frequency because this is actually AC, alternating current. And so power can either flow out to the rest of the grid through this box here, which I'll describe in a second, or it can go back to the inlet of the generator and bypass the grid when it's not needed. So these boxes in this diagram represent impedances. So here's one impedance, here's the other impedance. So an impedance is just, in AC terms, is basically just it resists the flow of AC current. It's like a resistor in a DC circuit. So basically, current flows out, and it's flowing through all these transmission lines, distribution equipment, the transformer I was talking about earlier. We're modeling these as resisting the flow of AC current. So just like a wire in a DC diagram can heat up as current flows through it, and it'll resist current flow, same thing kind of happens with all this distribution and transmission equipment in the AC world. And so we have the AC version of resistance impedances shown over here. And just like in DC, this is a circuit diagram. You can solve for the voltages and the current and the power at any of the different parts on this diagram, just like you would with the DC circuits that you've been looking at. So this gives us the connection of a single generator to the rest of the grid. But we really want to see how power flows between generators and between generators and the rest of the grid. So now we need to copy this diagram over for each additional generator that we have connected to the grid. So we would do that. And let's say we stack these together. And for each new generator, we do the same kind of diagram and draw them connecting to the rest of the grid. And now, using the tools of matrices and linear algebra, we can actually stack together the differential equations that we get from these circuit diagrams. And so we've got the swing equations, which model the power flow through a generator. And we have and we can stack together, using matrices and linear algebra, we can stack together all these differential equations that we get from each of these diagrams and simultaneously solve them to get all the states that might be of interest across the system. So now we can compute the voltages at each of the different nodes at any point in the power grid. We can calculate currents, we can calculate power. We can also look at how different changing loads could affect and stress the generators and can result in different accelerations on different generator rotors. And so using these tools, we can now model how the grid as a whole will respond to things like blackouts, which is what you'll be hearing about next.
Hello, my name is Tim Caldwell. I'm a recent graduate of Todd Murphy's lab. I'm going to be continuing what Alex was talking about, but now look at connecting multiple generators together and seeing how that interaction can cause a cascading blackout. So the diagram over here is a diagram of a power grid with 54 generators. The green circles are the generators, the dots are the loads, so these could be a small community or like a section of a city. And the lines connecting them, those are the transmission lines. So a lot of the electrical components that Alex talked about last time are abstracted away in just the lines we're using to connect the generators and the loads together. So since we have 54 generators, we need to, with our notation, we need to be able to distinguish which generator we're talking about. And so if we're going to use a subscript I, so if we're going to be talking about generator I, it's the acceleration of generator I's rotor depends on the inertia of generator I, and this equals the power from the prime mover that generator is inputting into the network minus the electrical power that is being consumed by the network from that generator. So we actually want this term, we want this side of the equation to equal 0. We actually don't want the rotor angle to be accelerating and deaccelerating. We actually want it spinning at a constant frequency. And so, for example, in North America, we want it spinning at 60 hertz. In Europe, we want 50 hertz. So we're actually going to look at what can cause this to speed up and slow down. But keep in mind that we want this side to be really close to 0 because we don't want it accelerating much. So m is going to be a constant. And we're going to be looking at short enough timescales that the power engineers are not changing what the prime mover is doing. So this term is also going to be constant. So the only term that is actually going to be changing with respect to time is the power being consumed by the network. And it turns out that this electrical power, it equals the summation of all generators J that are not equal to I. So we're going to be summing over all the other generators, not including the ith generator. And it depends on this constant term Aij, where Aij it depends on the electrical components between generator I and generator J. And so it's just going to be a constant. So let's not worry about it for this talk. And then with some approximations, it's times the rotor angle of generator I minus the rotor angle of generator J. So this is very interesting. This is, if we plug this term up here, we actually see that the acceleration of rotor I depends on the relative angle of rotor I with all the other rotors. So this is actually pretty interesting. In fact, let's suppose that rotor angle I is much greater than all the other rotor angles. So we're going to use a term leading in this case. So if generator I is leading, then that means that this term is greater than 0, which means this term is less than 0, and that probably is going to mean that the whole term is going to be less than 0, which means that rotor I is going to be deaccelerating. So it's going to be slowing down, which is sort of interesting. If rotor I has greater value than the other generators, it has a tendency to slow down. Now, if we look at the other scenario, where let's say that rotor I has less value than all the other generators, then we use the term lagging. So if generator I is lagging, this term will be negative, which makes this term positive, which makes this whole term positive, which means that the acceleration, that the rotor I is actually accelerating now. And so if rotor I is lagging behind, if its rotor angle is less than all the other generators' rotor angles, then it has a tendency to speed up. So we actually call this a synchronous machine. The power grid is a synchronous machine because just from the physics of connecting multiple generators together, it has a tendency to synchronize to a constant speed, to this term being 0. And that's because if a generator has greater value, it slows down, and if it has lesser value, it speeds up. Which is very neat, but we have one problem, which is if we have a large disturbance, so this could be another generator in the network failing, for instance. If we have a large disturbance, then then generator I might, for instance, end up having a very much greater value than the other generators. And so because it has greater value, it's going to slow down. And so it might slow down so much that now it's lagging more than it was leading before. And now that it's lagging, it starts speeding up again. And so it might speed up to the point where it's leading more than it was lagging. So we can have this oscillation where the oscillation is actually growing instead of decaying. And we call this the network destabilizing. And this is bad because when generator I starts accelerating quite a bit, there's large momentums on generator I, which will stress the generator. And so before the generator starts becoming damaged, power engineers will take it offline. So we're actually going to look at this sort of behavior across this full network shown here. We're going to look at 3 simulations. So in each of these 3 simulations, one generator has failed. And the generator that has failed is shown with a black circle. And as we integrate forward in time, as we solve this equation, some generators will end up will end up going unstable, and the power engineers will have to take them offline. And so we're going to go ahead and play that and see what happens. So we actually see that in this bottom simulation, even though the generator that failed splits the network in 2, no other generator ends up needing to be taken offline. And in this middle simulation, it actually ends up stabilizing. Part of the network ends up stabilizing and having good execution, while in this top simulation, the whole network blackouts. And so that is how a cascading blackout can happen.